Academy. Hi dear students, once again, namaste. So that's me, okay? So Trinath, the faculty of ACE Engineering Academy, like your analog circuits faculty. Students, like if you are thinking about the KPTCL program, ACE online platform, I believe that is one of the best platforms as a cream professors in India we have. And guys, the ACE Engineering Academy for KPTCL aspirants, what exactly we provide. We are providing the pre-recorded videos, the technology what I have shown you, like we have some glass board, smart board, 3D animations, 2D animations. See, we pulled our sources and resources to deliver the proper content in the less time, such a way that you can have a lot of time-saving techniques, dears. A lot of shortcuts you could be having for sure. Why? Because this is the competitive exam where you could able to solve the numericals mostly within 1 minute or maximum 1.5 minutes you could take max. But before 1 minute itself, you could be getting the answers if you really follow the techniques what the professors discussed. And of course, we have the exclusive online live batches. So like that, we have the pre-recorded videos and exclusive online live batches. So regarding the details, I'll be discussing at the end of this session. Is it okay, dear students, right? Now, if I enter into the part of analog circuits over here, right, KPTCL, the analog circuits, if you understand, as per the previous questions, as the previous papers of KPTCL, if you ask me, I have seen that most of the questions they repeatedly asked under the diode circuits, the transistors, the small signal model of amplifiers, and your operational amplifier circuits and wave shapings. And of course, almost like 3 to 4 questions I have observed as per the previous questions under KPTCL. So I understand electrical engineering students, in many cases, okay, they are facing a lot of issues in small signal model of amplifiers, even in the numerical solving while finding the gain, especially the gain calculations part. They're taking a lot of time, okay? So like, I mean to say they're drawing H parameters separately and they're taking a lot of time to solve those questions. So I decided that in this live session, I want to discuss about the small signal model of your amplifiers part with reference to the gain calculation. That is the 1 hour session we have. I could max complete the part of gain calculations because I need to do a lot of numericals, which makes you confidence. You need to get some conviction, okay? Once you get conviction, you can attempt any sort of exams, what I believe. Right, dear students? So here, the part of small signal model, for that purpose, I will be starting some basic prerequisites, which are very much important. Okay, so let me take a simple diode circuit and I start. Simple diode circuit and I start the small signal part. That will be connected to the transistors part. Then we'll do the examples. Then let us verify within how much time we could able to solve the numerical. Is it okay, dear students? So the important note, what you should recollect from the concepts of diode. See, let me go in detailed way, dears. So let me go with the first point, students. If I consider a PN junction, like if I consider a simple PN junction diode, right, we say this is our P-type semiconductor, N-type semiconductor, right? And this is the anode part, and this is the cathode. So this is, we consider the total diode voltage across the diode, and I say the current propagating through the diode. Let me say ID, correct? Now, can you please tell me, dear students, whenever anode voltage, if I say diode is ideal, okay? If I say diode is ideal, whenever anode voltage greater than cathode voltage, I could say diode is on. Correct, dear students? Or we say diode is closed, diode is on. Or simply, we could say diode is forward bias. If anode voltage greater than cathode voltage. In the similar way, if diode is practical, correct? If a diode is practical, I understand if anode voltage greater than cathode voltage plus some knee potential, or we say 0.3 volt for germanium or 0.7 volt for silicon, we consider that diode is on. Diode is on. If I say a practical diode, as silicon, the knee voltage is 0.7 volt, germanium, the knee voltage is 0.3 volt, correct? Mostly we consider those values. Now, dear students, in other way, how can we represent? No doubt that diode voltage is nothing but anode voltage minus cathode voltage, correct? The diode voltage must be anode voltage minus cathode voltage. So, anode greater than cathode, instead of using this word, could I say the diode voltage greater than 0? Because anode minus cathode greater than 0. Anode minus cathode is a diode voltage. So if diode voltage is greater than 0, no doubt the diode is forward bias. In the similar way, if the diode voltage is greater than or at least equals to, I could say 0.7 volt, correct? At least equals to 0.7 volt. We could say that diode is on. That means with respect to this scenario, we can go for the VI characteristics. So what we can understand from VI characteristics, if you ask me, students, what is the importance of the VI characteristics if you ask me? Let me consider a simple resistor I take, okay? Let me consider a simple resistor. If I say this is the voltage across the resistor, and if this is the current propagating through the resistor. See, assume when current is propagating indicates there is a closed path. There must be a closed path, right? And if I plot the graph between voltage across the resistor and current propagating through the resistor, no doubt it is representing the linear graph passing through the horizon. So what it is representing? Just a slope. Just a slope. It is having some slope. So that slope represents the resistive behavior here. That slope is representing what? The resistive behavior of a particular element. So tomorrow, if you give me a device, let me say some X, a device, and if I go with the characteristics, the voltage across the device, current passing through the device, and if I get the characteristic in this way, that characteristic is having a slope. Whenever slope exists, in the characteristics, a proper slope exists, I could consider that could be having the resistive behavior. Resistive behavior. This is what the characteristics representing us. What it is teaching us is very important. In the similar way, if I consider the case of a diode, right? If I consider the case of a diode, you know, dears, we get like ID is equals to I naught exponential the diode voltage by eta Vt, or we say Vt, correct? This is the diode current equation, or the relation between diode current and a diode voltage. When diode is on, this is the relation between current and voltage. What it represents, guys, no doubt, if I take the diode voltage and if I take the diode current, it is very clear that it is getting some exponential characteristics. It is nothing but what? Exponential characteristics. What this is showing, whether I connect a diode at any circuit, I just don't care. Whether I connect the diode at any circuit, I just don't care. Once current is propagating through the diode, let me repeat, once current is propagating through the diode, or if you say diode is on, or if you say diode is closed, no discussion, this should be the characteristics of a diode. As per the physics from our basics of electronics, the current voltage relationship across the diode, fine. Irrespective of the circuit, once diode is on, this is the graph. Keep this in your mind. Now you know what we are doing? I'm just connecting the diode in a circuit. Now you know what I'm doing exactly? I'm connecting a diode in the circuit. The circuit is biased with some resistor R, or take it as a load, okay? Take it as a load, it's okay. And I'm biasing through some DC voltage V. Yes, okay. Now no doubt, here, let V is applied I applied some voltage V. V is applied such that diode is conducting. Diode is on, or I could say diode is conducting. That means I'm applying some voltage. Fix it that diode is on, or I say diode is conducting. Indicates anode voltage greater than cathode voltage. Therefore, I could say this is the anode voltage, guys, and this is the cathode voltage, and this is what, dear students, the diode voltage, and this is the direction where the current is propagating, correct? And no doubt the same current could be propagated through the resistor R. No doubt, diode is conducting. Now, could you please find the voltage current relation in the circuit? Let me repeat, the voltage current relation in the circuit. Now, with reference to the circuit, I understand it is a closed loop. I think I can use Kirchhoff Voltage Law. So, if I use that, what I'm going to get here, the applied voltage V equals to the voltage across the diode Vd plus the current passing through the diode Id into R. Oh, interesting. Now, could you please let me know what would be the current Id, dears? What could be the diode current Id? So, here Id is equals to minus 1 by R into Vd, correct? Plus V by R. Oh my God, this is interesting. Id is equals to minus 1 by R into Vd plus V by R, or something equation we got, which is still representing the relation between voltage and current. Now, if I plot a graph, the same diode voltage Vd and the same diode current Id. If I plot the graph right now, the same diode voltage Vd and the diode current Id. Of course, this is the diode voltage with reference to the current passing through the diode, irrespective of the circuit. I just don't care where did I connect the diode. If diode is on, if diode is conducting, this must be the characteristics, no second thought. Yeah, this is a law we need to follow. In the similar way, that same diode is connected in the circuit. Now, with reference to the circuit, what is the characteristic equation I got is this. This is the circuit analysis, okay? This is the characteristic equation I got between the diode voltage as well as the diode current. Now, you know what your scientist suggested? For some convenience, okay, let me assume this voltage, you fixed it. Let me repeat once again, guys. Your scientist is suggesting that, let me assume you fixed that voltage. You made that voltage is constant. Diode is on, diode is conducting, but you fixed that voltage at a particular voltage. Indicates it is a DC, fine. In the similar way, let me assume this resistor, or you can say biasing element, or you can say the load, okay. Simply call it as a load. You fixed it. So you fixed the load or some resistor, you fixed the applied voltage. So whenever this is fixed, indicates this total ratio will be a constant value. Will be what, dear students? Constant. Now you know the y-axis, I think it is the current. X-axis, I think it is the voltage, and this is maintaining a constant. Oh my God. You know how it seems to be. Your scientists surprised that it is like y is equals to some x plus some constant c. Let me say it is like mx plus c. Oh my God. So if a diode is connected in a circuit, the closed circuit, I am getting the characteristic equation as a line. Oh, the characteristic equation is what, guys? Line. Y is equals to mx plus c. But condition, don't forget, you're supposed to fix the voltage here. You're supposed to fix the load or a resistor here at a fixed voltage, at a fixed resistor R. Okay, I got the equation like y is equals to mx plus c. And you know here the m is like a slope, and no second thought, it is like a negative slope. M is equals to minus 1 by r, a negative slope. Oh, so the straight line with a negative slope. So how could we draw, my dear students? So if I go in this way, it seems to be like this, correct? A straight line with a negative slope where here m is equals to minus 1 by r. Correct or not, dear students? Now could you please let me know what is this value? What is this value? That means whenever I want to find the x coordinate, the highest value, with reference to the 0 axis, I say id is equals to 0. If I take that, then Vd will be equals to V or V equals to Vd. Correct or not, dear students? Therefore, the highest voltage what a diode can support, the highest voltage what a diode can experience is the supply voltage. More than supply voltage, you can't get the response, you can't get the output. This is very important even in case of transistors. The highest output voltage of a transistor must be DC supply plus VCC or plus VDD. Even an operational amplifier, the highest output must be plus or minus VCC, that's it. That is, we call it as ideally saturation voltages. Guys, correct or not? In the similar way, what could be this highest current? We will be getting by putting Vd is equals to 0. If I put at this axis Vd is equals to 0, the highest current is nothing but V by R, the highest value I could say. Now, what did you understand from this? So what I understand, the very first important point here is, when diode is closed, irrespective of the circuit, whether I use the diode in this circuit or I use the diode in other circuit, I just don't care. When diode is closed, no doubt, this could be the characteristic or that could be the current equation of the diode. Whereas, if that diode is biased in a particular circuit with some external voltage V and through some biasing element or a load, some R, then this could be the characteristic equation with reference to the circuit, a diode circuit. So it is exactly representing that. With respect to the circuit, the response what I got, ID is equals to, what, dear students? Mx plus C with reference to the circuit. And diode is on, yes. Whenever diode is on, what could be the current propagating through the diode? What could be the current propagating through the diode? The current propagating through the diode is I naught exponential diode voltage by, take it as eta Vt or simply Vt, it's okay, eta, take it as 1, it's okay. So this is what exactly I got, guys. So this is the characteristic equation of a diode in the circuit. This is the characteristic equation because the diode is on. So if I represent this graphically, if I represent this graphically, what you scientists observed, see, diode voltage and we say diode current. Right, dear students? Now, no doubt, this is the exponential characteristics what we got when diode is on. In the similar way, with reference to that particular circuit, this is the line with a negative slope I got. And both are equal. So whenever both are equal, I think this is the intersecting point. Correct, my dear students? This is that intersecting point. Oh my God. Intersecting point. That means what? At that particular point, you are operating the diode with respect to the circuit. I repeat once again, guys. That is the point. I repeat, that is the point. You are operating the diode with respect to the circuit. Indicates what? I never get all these voltages. I never get all these currents at this moment. Why? Because you fixed this voltage. You fixed that resistor. As you fixed this voltage, you fixed that resistor. The current propagating through the diode is fixed value. Of course, constant temperatures must be taken. It's okay. Take it as a constant temperatures and everything. You fixed this voltage. You fixed that resistor. Indicates the current propagating through the diode is fixed. The voltage across the diode is fixed. That fixed point is the point I got here. I got a big salute to the scientist. That fixed operating point. Fixed operating point. So therefore, this fixed operating point is popularly called as quiescent point. Quiescent point, the fixed quantity in a variable quantity. We consider it as a quiescent, fixed point. Because of this fixed point itself, the quiescent point itself, I can analyze the dynamic behavior of a diode. We'll check it out that. If I really understand the dynamics, then I can easily go with the small signal model. I can solve a lot of numericals. But we need to be strong in the concepts, because concept will give you confidence. Confidence will give you command. Command in the subject. Command will give you the creativity. Correct or not, dear students? The base root is a concept. Try to spend some time for the concept. Enough, guys. You could be rocking in any exams. Right, okay? Now anyways, you got the point or not? The quiescent point we got here. And don't forget, I won't get all these values. That means, practically speaking, if I plot the graph, the VD value and ID value, if I plot the graph, I don't get this line. I don't get this equation. I don't get this exponential curve. When I can get this exponential curve, if diode voltage is variable, when I could get this exponential curve, if diode current is variable, is it variable? No, no, you fixed it. You fixed it. They are not variables. They are fixed. You fixed it. You fixed it. The current propagating through the diode is fixed. That means you are getting just a point over here. That's it. Only a point, which is a quiescent point. You won't get this graph. You won't get that graph. You fixed it. Just for our reference purpose, I'm just drawing this just to analyze where exactly both are meeting, where exactly that fixed point I am going to get. Understanding or not, dear students, right? That is the fixed point I got. And that fixed current, we consider it as quiescent current of the diode, and this fixed voltage, we consider it as quiescent voltage of the diode. So what it represents, guys? This voltage is VDQ, this current is IDQ. Oh. So if I want to get the quiescent point, first thing, some biasing elements are needed. Some external biasing elements are needed. Second, a DC voltage is needed. Why DC? If it is fixed, then only V by R will be fixed. Then only Y equals to Mx plus C is justified. So a DC voltage is needed. Second is a fixed, it's the biasing elements are needed. Okay, so that is the reason why I believe you study in analog circuits. To select the quiescent point, I need biasing techniques. To make that quiescent point stable, I need stability techniques. Correct or not? That's from your transistors. Fine, but the root cause is a diode. Correct or not, dear students, right? The dynamics begin from here. Anyways, guys, I believe you got some clarity over here. So this is the fixed point. I got it as a quiescent point. That is, this is the point exactly we are operating. Now, what happens here? The practical observation given by the scientist is, students, if I consider the diode characteristics, I say VD, and if I say ID, if I go with the diode characteristics, it is an exponential graph. Correct or not? Let me draw properly. It is an exponential graph. It is an exponential graph. So if a single diode is there in a given circuit, I can easily solve that circuit. It is fine, okay. But if 3 diodes we have in the circuit, 5 diodes we have in the circuit, 12 diodes we have in the circuit, just you think, a lot of iterations are needed. A lot of repeated process we are supposed to go to find the answer because of this exponential characteristics. It is a huge time-consuming process, which is not advisable. See, we are the guys of circuit analysis. So we are supposed to save the time, engineers. We are supposed to save the time. Correct or not? So you know what? Your scientist analyzed that. Students, between the current, let me repeat, between the currents, I say 0.1 milliamperes to 10 milliampere. Listen my language carefully, guys. Between the currents of 0.1 milliamperes to the range of 10 milliamperes under silicon, what your scientist has done? He has just, he processed this negative slope straight line. We consider this as a DC load line, okay? With respect to the circuit, I got it DC load line. Why? Because a DC, I am supposed to fix the voltage there. Supply must be fixed, the DC value. And by fixing the resistor value R, I got this straight line. V by R, I got this straight line. That is, it is popularly called a DC load line, okay. That is not my major task here, okay. Finally, with reference to this negative slope straight line, DC load line, and VI characteristics, guys, we got the Q point, right? We got the Q point, right? You know what your scientist suggested? Just draw a tangent here. Let me repeat, simply draw a tangent which is propagating through this quiescent point. Draw a tangent which is propagating through the quiescent point and meet at some particular voltage on the x-axis, such that there will be only two lines over here. Let me say this is the line A, only two lines, straight lines. This is like line B. Okay, if I get the lines in this way, what is the advantage? Then, you know, the graph is like this. There exist only two lines, dear students. One is line A, the other is line B. Only two lines I got. What is the advantage? The first advantage, this is the graph which is almost seems to be like a linear after this particular point. As after this point, this is like a linear, indicates I can go with the slope. Oh, yes. Whenever a straight line or whenever a line which is having a slope, its characteristic behavior is a resistance. So if I know that diode is a resistor or a diode behavior is like a resistance, I think I need not to take more time to solve any numerical, because I know that diode is behaving like a resistance once diode is conducting. Oh my God. Whereas here, due to that exponential characteristic, lot of iterations I need to proceed. Complications I'm increasing, which is not advisable, I believe, in this competitive world. Within short span of time, how fast you're getting the output, that is what the technology we need today, right? The technology improvements. So like that, I think it is like only two lines I have. One is the zero line. I mean to say current is zero, no discussion. Now, if you are expecting any current in a diode, you know, that is representing the diode behaving like a resistor. So, off switch, resistor, off switch, resistor. Diode is off, diode behaves like resistor. Diode is off, diode behaves like resistor. Oh my God, how simple it is, guys. Then I'm surprisingly, I can use that superposition theorem. Don't forget, guys, diode is non-linear. But if I can make it possible in this way, yes, I can use superposition theorem for diode. I can use Thevenin's. I can use Norton's. I can use the circuit analysis to solve the diode circuits. Sir, is it your wish to draw the tangents in this way? Interesting part. You know, is it successful or failure if you ask me? Students, with respect to the original characteristics, if I find the diode voltage, and with respect to this principle, if I find diode voltage, let me repeat, if a diode is operating in a circuit, by using this characteristics, by using this VI characteristics of exponential current equation, if I solve the circuit, I'll find some diode voltage as X. Now, by using this, I mean to say the linear response, the linear model, it is almost like a linear model, but not linear exactly. I'll tell you that. The two-line model, okay, the slope model. If I find the diode voltage in that circuit, I'm getting the value as Y. So X, the diode voltage, Y, the diode voltage. And you know the difference between those two voltages is almost like 50 millivolt. Let me repeat how much, guys? 50 millivolt. When diode current is in the range of 0.1 milliampere to 10 milliampere. Oh my God. That means what? If the diode is conducting in the range of 0.1 milliampere to 10 milliampere, then the result what I am getting when I use the diode in a circuit through this exponential characteristics, and the result what I am getting when the diode is used in a circuit through this linear characteristics, the result is almost similar. Just a 50 millivolt difference, I don't think so that is a huge difference in our circuit analysis. Correct or not, dear students? Then why should I waste my time to use this exponential characteristics? That is engineering. That is the intelligence of engineers. A big salute to those great personalities. Oh my God. So if I want to get a piecewise linear model, I realized I am supposed to go for the quiescent point analysis. I believe you got the point. Clear picture or not, my dear students? Yes, this is the first structure we got, the piecewise linear model. Therefore, guys, if I go with the circuit behavior, that is the diode voltage, and I say the diode current over here, students, you know, this is, I'm sorry, we can go for the two lines, that is piecewise linear model, we can move in this way. Correct or not, dear students, right? Right? And no doubt, take it as like a load line, we say DC load line, say in this way, the DC load line we have. Now this is the quiescent point. You are operating the circuit, the quiescent point. Now can you please let me know, dear students, this is the diode voltage, where exactly you are operating, and it is quiescent, and this is the diode current, where exactly you are operating, which is a quiescent. Understanding or not, dear students, right? Now you know, if I could go with the equation here, so what is this voltage? Let me say this is a V gamma. We say cut-in voltage. I say cut-in voltage, right? Some 0.3, like 0.7, 0.3 for germanium, almost 0.7 for silicon, cut-in voltage. Now, from here, the voltage VDQ we are supposed to find, correct? From here to here. From here to here, we are supposed to find the voltage VDQ. Could you please find what is the value of VDQ? Simple logic. The voltage VDQ is equals to V gamma plus, yes, up to here, there is a voltage drop, V gamma, plus this voltage. This total voltage is equal to this voltage plus this voltage. Sir, to find this voltage, I think there is a conduction, indicates current is there. I think there is a slope, indicates resistance is there. Whenever current, resistance exists, I think voltage exists. V is equals to I into R. So I could say it is plus ID Q, thank you so much. ID Q is correct. Into the diode resistance I say, let me say it is RD. That's it. So the quiescent point is equals to the cut-in voltage plus IDQ into RD. Oh my God. So this is the diode voltage I got exactly. So what exactly the equation, dears? See, this is my PN junction diode, correct? So this is P-type semiconductor. This is N-type semiconductor. So this is what? Anode, and no doubt this is what, dears? Cathode. So no doubt this would be the voltage, I say VDQ, because that is the quiescent point exactly you're operating. This is plus, this is minus, because anode voltage greater than cathode voltage, and this is none other than the current propagating, I say IDQ. Now, with respect to this equation, could I draw any equivalent circuit here? Yes. VDQ is equals to V gamma. V gamma indicates it must be positive voltage. V gamma plus current into resistance. Already current is there. So I believe I could produce some resistance over here, RD. So as this PN junction diode is on, yes, this is simply replaced with on switch. Indicates what? At this operating point, if you ask me how diode is performing, guys, the diode is performing, you know, with a just voltage and some resistance. This is voltage drop, okay? Say 0.7 volt or V gamma, it's okay, fine. And this is some diode resistance RD. This is anode and this is cathode. Oh my God, how beauty we got this response. Now I believe you understood the point or not. So till now, what I have done, I am applied some external voltage. Due to some external voltage, of course through some biasing element R, you can call it as a biasing element or a load, option is yours, okay. You fixed the quiescent point. With respect to the quiescent point, where exactly my diode is operating, I got an equivalent circuit of a diode. Oh, equivalent circuit. and as you fixed the points, quiescent point indicates it must be a DC equivalent circuit, DC equivalent circuit, because you fixed everything under a DC, I mean it's a fixed voltage. So this is the circuit what we got as an equivalent circuit. Now for this diode, I am interested to apply the small signal, because my target is what? The small signal model. Now I am interested to apply the small signal. Can I? Yes. Let me apply the small signal. Commonly, students, if you hear the word small signal, you know, you can take, it is almost like, I mean to say, in the range of like millivolts, guys. Mostly you can take it is in the range of millivolts. Very few cases, maybe microvolts. Do one thing then, let me take it as like microvolts to, I could say, millivolts. The small signals, very small signals. Let me say the sensor signals, wireless communication signals. Let me say my voice, okay, my voice. 0.1 millivolt to 0.8 millivolt, mostly it is in the range. So everything we consider them as what, guys? The small signal. Now, this small signal is applying to the diode. Now I want to ask a small question, guys. If this is a diode, now no doubt there is a closed switch. Let me say this is some R, there is a closed switch. Assume I am giving a sinusoidal wave at the input of a diode. I am giving a sinusoidal wave. So this is positive IC, negative, positive, negative in this way. So this is 5 sin theta. Okay, that is the voltage I have provided to the diode. Now in the positive half, I repeat, in the positive half. So whenever I say positive half, now speak out here, only positive signal is applied to the diode. Only positive signal is applied, because I am considering the positive half. What is the highest peak value? 5 volt. The highest peak is what? 5 volt. What is the minimum voltage? That means this anode voltage. What could be the minimum anode voltage I need to on the diode? At least greater than or equals to 0.7 volt. I think this 5 volt is greater than 0.7 volt. So diode could be on. As the 5 volt is greater than 0.7 volt, so diode could be on. If diode is on, diode will be conducting, okay, fine. I believe you're getting the point, because anode voltage, at least it must be greater than 0.7 volt of cathode voltage here. Therefore, diode is on, no doubt, I am getting some conduction, fine. But now for the same circuit, let me assume the sinusoidal of my voice. Of course, my voice is not exactly sinusoidal. There exists a lot of fluctuations. For an ideal case, assume it is my voice, 5 sin theta. My voice, as I discussed, it is a small signal. Assume it is in the order of like a 5 millivolt, okay, 5 sin theta in the order of like millivolt. You know what students are doing? They're forgetting about this millivolt. They're not taking seriously about this millivolt. They're saying that this is positive, this is negative, this is positive, this is negative. So in the positive half, diode is on. In the negative half, diode is off. This is the nonsense, okay? If you want to on the diode, anode voltage must be at least greater than, at least equals to 0.7 volt plus cathode voltage. The anode voltage, what you are giving, guys, 5, maximum value itself is 5 millivolt. So the highest anode voltage what you are providing itself is 5 millivolt. What is this? Can you say that the 5 millivolt will switch on the diode? The 5 millivolt? It is absolutely lesser than the 0.7 volt. So anode voltage, see, this is the case, right? Anode voltage at least greater than or equals to 0.7 volt plus cathode voltage. This is the case, right? So this is the cathode voltage, and this is what, guys? Anode voltage. Now the cathode voltage is 0 because resistor never store any charge. If I have a capacitor, okay, that is different. It is resistor, never store any charge. So there is no voltage across here, say it is a 0 volt, okay, fine. Now cathode voltage is 0. indicates if anode voltage greater than or equals to at least 0.7 volt, I can get a diode to be conducted, correct? Now interesting fact is the anode voltage, the maximum value, the peak value itself is 5 millivolt. Is 5 millivolt greater than or equal to 0.7 volt? No. So what it represent? My diode is off. My diode is off. Indicates what? If I provide a small signal alone, let me repeat, if I provide a small signal alone, diode won't conduct. If I provide a small signal alone, diode won't conduct. Diode won't conduct. If I provide a large signal in the order of volts, okay, fine, diode could be conducted and I may get it as a rectification. But I am giving the millivolt, microvolt, a small signal. Alone, diode won't conduct. Yes, okay, then what should I do? That is what the procedure we have done till now. So what should I do? If you want to propagate a small signal through the diode, if you want to propagate a small signal through the diode, what you're supposed to do? The scientist suggested that first diode should be on, because a AC signal alone cannot on the diode. So I just don't care what you do something that diode should be on. Indicates what? First, give some DC biasing technique. Let me repeat, use some DC biasing technique. Use some DC biasing technique. That is the circuit. Let me say this is the circuit. Use some DC biasing technique. Say, take some biasing elements, take some external DC supply. Due to that, take care, diode should be on. Indicates you selected the quiescent point of the voltage, you selected the quiescent point of the current. Now you got clarity that diode is on. Diode is conducting. Yes, diode is on, diode is on. Surprisingly, my diode is conducting. My diode is conducting. Now, to that circuit, apply the small signal. This is what he suggested. To that circuit, apply the small signal. Because small signal alone cannot decide the biasing of a diode, whether it is forward bias or reverse bias. Small signal alone cannot decide. The quiescent point will decide. That is why the selection of quiescent point will decide the operating region of my electronic device. Whether it is a transistor, whether it is a BJT, whether it is a MOSFET, whether it is an amplifier, whether it is a diode, quiescent point will decide the operating region of a transistor or an electronic device, our device. So quiescent point is first. Before applying a small signal, just bias the transistor, bias the amplifier, bias the diode with DC, external DC supply, and through some biasing elements. My diode should be conducting, my transistor should be conducting, my amplifier should be conducting. Once you got confirmation that my device is conducting, then apply AC on to that device. That is why for amplifier, first you switch on the supply to the amplifier. Once it is conducting, my amplifier is on, then only you connect the mic, then only you speak. Because the quiescent point will on the device, not the mic. If I switch off the supply to the amplifier, you can check it out any amplifier, even the mic, what I am talking right now, if I remove the battery from the amplifier, even though I speak, my amplifier don't conduct because it is a small signal. It is not having any energy to on the diode because minimum knee voltage is needed. Correct or not, my dear students, right? This is the beauty. That means for the same circuit, guys, for the same circuit, see this is the circuit. This is the circuit we have provided, right? For the same circuit, I am just interested to apply some AC signal, which is a small signal. This is a small signal. So no doubt, this is our circuit, guys. This is the circuit, and here we have the load. The circuit, we have the load. Okay, dear students, this is like P-type, N-type, and of course that is anode, cathode. Yeah, everything is same. That means if I go with the characteristics, dear students, if I go with the characteristics, so this is the diode voltage, this is the diode current, Now, students, you know, the two lines up is wise, linear model if I proceed, and here the quiescent point through some biasing techniques, yes, I have done. Now, this is what, dear students, the quiescent voltage. Now, here a scientist suggested to apply the AC signal. That means we applied AC onto the quiescent point. Yes, this is the AC signal. That is the AC signal you have applied onto the quiescent point. So this is like the highest limit and this is the lowest limit of AC signal. Yes, even with the positive half of AC, my diode is conducting. Why? Because my current is there. Even for the negative half of AC, my diode is conducting because current is there. Now this is what, dear students? This is nothing but VDQ. And this is the lowest value and this is the highest value. So yes, my diode is conducting. In the similar way, this is the highest value of current. This is what, dear students? Quiescent point. I could say this is I, D, Q, and here this is the current. This is the current. So I'm very happy to say my diode is conducting. Oh my God. So first I made the selection of Q point through the DC biasing techniques. After that I applied the AC signal, so called the small signal, due to which my device is conducting. Now tell me, dear students, my small signal is propagated through the slope of characteristics. Please understand. The small signal, I repeat, the small signal is propagated through the slope of characteristics. Slope represent what? Resistance. Oh my God. That means what? When a small signal is propagated through a diode, it is behaving like resistance. Very simple logic. It is behaving like what, dear students? Resistance. Simply behaving like resistance. Guys, okay? So that is the reason why whenever a small signal is propagating through the slope, then I can find the resistance is equals to like 1 by slope. This is what in the diodes you will come across, the resistance. And of course that is the AC signal what we have provided, which is a dynamic. In the slope, in that characteristic, it is behaving like a dynamic. That is why it is like considered as AC resistance, or we say dynamic resistance. AC resistance, or we say what here? Dynamic resistance. Because slope is nothing but current by voltage, Y by X, right? So the resistance is equals to voltage by current, 1 by slope. So what could be the resistance value we are supposed to get, my dear students? What could be the resistance value? So like if I say slope is equals to, so simply dID by dVd, or as it is AC, I could say IAC ID by VD. Therefore, the AC resistance, or we say dynamic resistance, which is nothing but what, dear students? 1 by slope, which is dVd by simply what, guys? dID. Right? So in a very simple way, if I go with the current, what is the current when diode is conducting? ID is equals to I naught exponential diode voltage by eta Vt. So could I differentiate, guys, with respect to Vd? If I differentiate, you could be getting I naught exponential Vd by eta Vt into 1 by eta Vt. So I naught into exponential Vd by eta Vt is nothing but what, dear students, like, which is Id, right? Sorry. Yes, this current is equals to Id. So it is like Id by eta Vt. If you could eliminate eta, okay, eta equals to 1, then Id by Vt. So current by voltage. Oh my God. This is what? AC. AC. This is what, guys? AC conductance. AC conductance, which is depending on ID, where what is this ID? Is this ID. What is this ID? Quiescent point. Oh my God. So this AC conductance depends on a DC Q point. Oh my God. So here G AC directly proportional to the quiescent current. the quiescent current. Great. The quiescent current, dynamic. That is why I consider it as a dynamic. Therefore, what could be RAC, dear students? RAC is nothing but 1 by conductance, which is equals to how much I will be getting, dear students? Eta Vt by IdQ. If you could eliminate that eta, you will be getting it as Vt by IdQ. Dynamic resistance. So dynamic resistance depends on what, dear students? Quiescent point. Quiescent point. That is why if I apply a small signal, therefore, if I apply a small signal, dear students, if I apply a small signal, simply I could replace the diode with a resistance. Let me repeat, guys. I could replace a diode with a resistance. That resistance is nothing but what? RAC. Dynamic resistance. So for a DC, how the equivalent circuit we got? For AC, it is as simple as like dynamic resistance. This is the beautiest part. Now if I go in the similar way for case of transistors, then how can we draw the equivalent diagram and how can we find the gain? I'll be discussing. So just go for the break for just 2 minutes, guys. Come with a very fresh mind. Just, I believe, take a breathing space just for 2 minutes, okay? We'll be coming, right? Yes, my dear students, come back, right? So till now, what did we understand? Just a small overview, okay, guys? So for diode, when a small signal need to be provided, initially diode need to be biased through dash supply. Initially, diode need to be biased through dash supply. When I provide, the small signal, what supply need to go to on the diode? Yes, guys, you are perfectly correct. We are supposed to apply the DC supply through the DC biasing technique. Superb. The DC biasing is must to select. The DC biasing is must to select, maybe for a transistor, maybe for an amplifier, or maybe for a diode. Perfect, you're perfect. To select quiescent point, or we say Q point. Very interesting. Very interesting. Without external DC bias, we can provide a small signal to the diode for proper conduction. Without need of any external biasing, can I apply a small signal to the given diode or a transistor? No, you can't. The small signal alone cannot bias the device. So answer is no, you can't. You can't. Next, therefore, the final conclusion if you ask me, hence once diode conducts, the small signal model could be simply a resistance. RAC is equals to 1 by diode resistance, VT by IDQ. So RAC is nothing but what guys? RD, that's it. How simple this is. Now in the similar way, guys, just mostly 20 minutes, please bear with me, just 20 minutes, because if I start directly in this way, I don't think so you'll get a clear picture. That's the reason why I have taken the support of a diode. By that I believe these concepts will become very easy for you. Just spare 20 minutes, okay? By that I can wind up this part and we can do some numericals, okay? Right, so in the similar way, if I consider the bipolar junction transistor, yes, we know that it has input characteristics and it has output characteristics. So if I go with input characteristics, let me say, like input current, if I consider it as an IE, and input voltage, if I take it as VBE. So from the analysis of transistors, I believe you know that almost the similar to the diode characteristics you will be getting, but variable values will be getting, because bipolar junction transistor, input characteristics are drawn between input voltage and input current by keeping output voltage constant. Correct? Output voltage constant. So I'm supposed to keep some output voltage constant. So the three-dimensional, I mean, three variables we have. We have three variables. I'm drawing in a two-dimensional way. That's why I'm putting some output voltage constant. We'll be getting some characteristics in this way. So output voltage, let me say some VCB1, I say VCB2, and simply VCB3 by changing the output voltages. Yes, this is the graph. Now, speak out guys, even the similar behavior, yes, the same. I can go for the quiescent point selection by drawing the load line. Yes, the same behavior, the same scenario. I could draw the load line. So either this is one operating point, this is another operating point, this is another operating point. I have three operating points. Out of three operating points, you could select only one operating point. So select one operating point, then draw the tangent, then you will be getting the piecewise linear model. Then if you get that piecewise linear model, no doubt you will be getting the slope. Once you get the slope, no doubt to say guys, what I'm going to get? Yes, I can apply the small signal model of a transistor. Correct? So if I select just one operating point, let me say this is VBE and this is simply IE, okay? Now, dear students, if I move in this way, right? Move in this way, say like in this way, like that. If I'm getting different voltages, like even maybe from here, like that. So if this is the load line, if I select the quiescent point over here, then no doubt here I'll be getting the slope. Because here I could apply the AC signal, that will be acting like what, dear students? Slope. Whenever I'm getting a slope, no doubt I will be getting what? Resistance of the system, resistance. And this resistance inversely proportional to diode current. The resistance inversely proportional to diode current. In the previous case, the diode current is what? Y-axis, correct or not, dear students? I believe you're understanding. This resistance, the resistance what I got here, because of the slope, the resistance what I got, RAC, is inversely proportional to what, dear students? The y-axis current, that is a diode current. In the similar way, the resistance here, yes, the resistance here, what I'm going to get here is inversely proportional to the emitter quiescent point current. Just I'm comparing guys. Okay, in a very simple way I'm teaching this. Very simple way. Don't make your life complicated. Okay guys. So the resistance is inversely proportional to the emitter current. What is that emitter current? The quiescent point current what you're considering here. Correct or not, dear students, right? So this could be represented in this way. R is equal to simply the thermal voltage by IEQ. Simply thermal voltage by IEQ. resistance inversely proportional to emitter. So I could say this is AC emitter resistance. What is that, guys? AC emitter resistance. So RE could be taken as what? AC emitter resistance. Oh, this is fine. AC emitter resistance, fine. In the similar way, guys, if I go for output characteristics, of a transistor, I believe you have remembered this. This is like output voltage, let me say VCB, and output current, say this is the IC. So in case of forward active, if you ask me, like ideally we got it as a straight line. Have you remembered or not? In case of forward active, this is the case of forward active. I believe you remembered. In case of forward active or in case of transistor, especially the BJT, output characteristics are drawn between output voltage versus output current by keeping input current constant. By keeping what, dears? Input current constant. So I say if input current is IE1, here it is IE2, here it is IE3, here it is IE4. Output characteristics are drawn between output voltage versus output current by keeping input current constant. Now, you know, this is the graph I got. Could you please let me know, guys, what is this graph representing? If this is voltage and this is current, and I am getting the line parallel to x-axis, a straight line parallel to x-axis. I am getting a straight line parallel to x-axis. What it represent? Superb. Even the voltage changing, current is not changing. So the current is independent on voltage changes. Hence it is a current source. Oh my God, constant current source. What source, guys? Constant current source. Oh my goodness. Therefore, here I could represent it as a constant current source. Where exactly this constant current source is getting? At the output side. Oh my God, what are characteristics? The characteristics are teaching me that this is a current source. So BJT is a constant current source, or we say current source simply. Therefore, BJT is an active device. Oh, I believe that is the reason why I think they are calling it as a forward active. Yeah, fine. Anyways, it is a current source, fine. And this is what current, guys? Output current. Yes, this is the collector current, I say, output current. This is the output voltage VCB. So, output current. And no doubt, depending on what input current, Nadia, this is IE, right? IE. Depending on what input current. So, what is the relation between IC and IE? So, IC is equals to alpha times IE, correct? In forward active, it is alpha F. Therefore, we could represent it as like alpha F times IE. Oh. Also, I believe you know that IC could be represented in this way, beta F times IB. Correct? IC is equals to alpha F times IE, or IC is equals to beta F times IB. So the same current you can represent in this way, beta F times IB. F represents forward active. It is under forward active. In case of diode, did I get the response in this way? No. So diode you can't compare with an active device. Diode is a passive. The transistor is an active. Interesting. In the most practical way, if you go through the transistor, see, in a most practical way, I believe due to the early effect, due to what, dear students? Early effect, most practical way, if I move, you could be getting the graph in this way. Correct or not, dear students? A slight slope you could expect over here in the forward active region. Because of what? Early effect, early effect. So whenever I'm getting the slope, no doubt here, I think I can find the slope here. When I go with the slope, I believe I can easily find the resistance, dynamic resistance, or we say AC resistance. And this is depending on what current? IC. So this resistance at the collector proportional to 1 by ICQ. Same concept here. Let me not repeat. Same concept. RC, or we say collector resistance, or output resistance, I could say let me say output resistance R naught directly proportional to what, guys? 1 by ICQ. This is what because of early effect. You please recollect the concepts of early effect. Okay, therefore, this resistance could be represented in this way. Early voltage by simply ICQ. Simply early voltage by ICQ, which is the output resistance. So I'm so happy to say that at the output side, yes, it is behaving like a current source ideally, but practically it is not only having current source because of early effect, it is having some resistance. That resistance, because of current source, resistance need to be represented in parallel. Therefore, I could say this is R naught. Oh my God. So this is the output behavior under small signal, because it is a dynamic resistance, the small signal resistance here. The small signal resistance. Guys, I believe you're getting the points or not, dear students, right? So, if I draw the equivalent circuit, see how I'm getting all these circuits? From the analysis of characteristics. That is the reason why characteristics of a diode, characteristics of a transistor play a very important role, VI characteristics. Okay, so dear students, now could you please let me know here? So if I say this is our BJT, see bipolar junction transistor, right? So if you ask me the small signal model, if you ask me a small signal model, a very simple small signal model. If you ask me the small signal model, you know how can we draw? Students, this is the base, and base to emitter there is a resistance, because this is the resistance connected to what, dear students? Emitter. You know that N type, P type, N type. This is emitter, this is base, and this is what, guys? Collector. Now tell me, dear student, this is emitter resistance. We could say RE, dynamic, AC resistance, dynamic resistance. Now note that this is what? Collector. Remember or not? Collector with reference to the base, it's a current source. Clearly I discussed. A current source, yes, it is a current source. Yes, fine. The current source, constant current source, it is an active device. So if this current, depending on the base current, you can represent this as beta F times simply IB. Or if it is depending on the emitter current, alpha F times IE. Alpha F times IE. But consider in the forward active, because this constant current source clearly represented in the forward active, not in other cases. I am talking about only forward active here. Now, this is what, yes, the collector, and this is what? The emitter. And there is an output resistance. So you can go the output resistance over here. I could say this is R naught. That's it. That's it. But see, this KPTCL, like 1 mark questions, you need not to go, they don't ask very complicated tasks. They ask very simple numericals, guys. Very simple numericals. Even in the previous KPTCL questions, they have asked some amplifier gain calculation. Very simple numericals. So you can avoid R naught. So you can take a simple ideal model. Ideally, you can take R naught is equals to infinite. That's it. Ideally, you can take R naught is equals to infinite. That is, early voltage is equals to infinite. You can skip this R naught. You can skip this what, dear students? R naught. That's it. So this is a very simple model here. But my condition, don't forget. If you want to use this for small signal, first thing is what? You should apply the DC supply. First of all, you should on the transistor by the DC biasing technique. By using DC biasing technique, you should on the transistor. First point. Second point, through some biasing elements, you should select the quiescent point in the forward active region. So first thing is what, dear students? Through DC biasing technique. Through DC biasing technique. Speak out, dear students. We should select what, dear? Quiescent point. We should select Q point in forward active, which is very important. Through some DC biasing techniques, we are supposed to select the quiescent point in the forward active. I need not to repeat this again, because already I have shown you in the case of diodes. Okay, my dear students, right? After that, after selection of quiescent point in the forward active, you are supposed to give the AC signal. that AC signal would be propagated inside the system where we could be getting this amplification. Understanding or not? So this is an absolute, a simple small signal model which is popularly called as RE model. I repeat guys, RE model of BJT. Very simple model, RE model of BJT. Understanding or not, dear students, right? So let me show you guys. See here. When we need to calculate, when we need to find or calculate the gain of an amplifier, the gain of an amplifier, whenever we are supposed to find the gain of an amplifier, the very first point is what, dear students? Q point must be inactive. In the BJT, Q point must be selected in the forward active. And the second important point here is there must be no external capacitors must exist. No internal capacitance, no external capacitors must exist. What is the reason? I believe I'll discuss later, okay dear students, not now, because it takes a lot of time to discuss about the capacitance part. Fix it in your mind, in future classes you will be getting that. So fix it in your mind that external capacitors should never exist. They should behave like a short circuit. So whenever you want to find the gain of an amplifier, the very first point is you should select the quiescent point in the forward active. That is through the DC biasing techniques. Second point, if any external capacitors exist, they should be replaced with a short circuit. So they should be replaced with what, dear students? Short circuit. You please repeat this number of times. External capacitors must be replaced with a short circuit, and the quiescent point must be selected in the forward active region through the DC biasing techniques. Then only you can find the gain of an amplifier. Understanding, my dear boys and girls? In future classes, you will be getting for sure. Why should I do that? That reason. But in a short span of time, we can't discuss that. Now, so I'll do one small example, guys. By that, I believe you get some conviction. Students, very simple circuit. Let me take, I think already I have, okay, no problem. Let me take a simple transistor. Very simple transistor, guys. So this is what? RC. And here, externally I am connecting, this is like RB. Yes, here, through the capacitor, I am providing the input voltage. And through the capacitor, I am taking the output voltage, V0. And here, the DC supply, VCC I am providing. So this is the transistor. So, dear students, external components. See, outside the circle, everything is external. Inside the circle, that is a transistor, unique behavior. So externally, we connected some capacitor, resistor, capacitor, DC supply, biasing elements. What, dear students? Biasing elements. Now I am supposed to find the gain. I am supposed to calculate gain. Now tell me, dear students, once I am supposed to go for the gain calculation, no doubt, we need what, dear students? We need AC circuit. We need what, dear students? AC circuit, AC equivalent circuit. Because through DC circuit, I already biased the quiescent point in the forward active region. I am so happy. Now I don't need any DC support because already DC existing. Now with respect to the AC, how the response goes, that I am supposed to calculate here. So I am going for AC equivalent circuit because I need exactly the AC characteristic behavior, which is the signal, how it is getting amplified, that gain I need to find. Now if I go for AC circuit, now dear students, please tell me, see, this is our transistor. This is our transistor. So this resistor RC, here VCC need to be grounded. Why? Because the DC voltages must be short. I need only AC circuit. So voltage must be replaced by short. Current must be replaced by open. So DC voltage must be short, which is grounded. Therefore here, we could connect what, dear students? RC, which is grounded here. In the similar way, here, we can connect what, dear students? RB, which is grounded here. Correct or not, dear students, right? And no doubt here capacitor must be short. We can apply the input voltage, and this is the ground, and even here the capacitor is short, so here we can take the output voltage. Is this correct or not? Simply correct or not, dear students, right? External capacitors must be taken as a short circuit. Now, by drawing the simple RE model, what is that RE model we got here, dear students? So, if I go with an RE model, so this is RE, and here this is like the current. Why? Because current always move from collector to emitter in case of NPN transistor. This is what? Collector, and this is what? Emitter, and this is what? Base. That means, yeah, inside this circle, what I have the equivalent diagram is this. Because the slope, because of that slope, I am getting this constant current source with respect to the output part. So it is what, guys? Beta f times some IB or IE, it's okay, fine. Alpha times IE, it's okay, fine. Correct or not, dear students, right? Now, external components, that is, to the collector, RC is connected with respect to the ground. So that is the place where you're taking the output. That means to the collector, this RC is connected. This RC is connected with respect to the ground. So I could say this is V0. In the similar way, this emitter is with reference to the ground. So I could say this emitter is with reference to the ground. In the similar way, the base is connected to RB with respect to the ground, and to the same base, Vi is provided. Indicates this base is connected to RB with reference to the ground, and to the same base, Vi is provided. That's it. So this is the circuit. I repeat, guys, this is our circuit. Understanding or not, yes, base, emitter, and your collector. Understanding or not? Now, could I redraw the same circuit in this way? You know, what method I follow is, instead of drawing the circuit separately, onto the same transistor. See, this is the transistor. This is the transistor, correct or not? So, onto the same transistor, for emitter, I am connecting RE. Now, this is emitter. And for collector, I am connecting I. So, this is collector. And simply, this is base, where there is no voltage drop for AC signal, because I am considering everything is under AC. That's it. The same circuit I am drawing in this way. Inside the circle, what is inside the circle, I am drawing in this way. By that I can save a lot of time instead of drawing all these things separately. We are going to the competitive exams. We need to save a lot of time dates. Correct or not? Sir, why there is no drop? Because I am going for AC signal. For AC signal, no drop. Why? Because the AC signal is propagating in the slope. There is a drop only for a DC. 0.7 volt DC is a drop. For AC, no drop. Why? Because the AC signal is propagating through the slope. In the slope, positive half, negative half, both are propagated. If positive half, negative half, both are propagated, no drop. So no need to take any drop here. That is the reason why I explained you this much. Okay, dear students, right? And this is our collector, this is emitter, this is the base. Now to the base, what I have connected here, dear students? To the base, simply connected what? Resistor, which is RB, and this is Vi. To the emitter, what I connected? Just simply ground. To the collector, what I have connected? Simply it is what, dear students? RC. And this is V0, it's over. V0. Guys, okay? So you can take it as what, dear students? Beta f times like IB. And what is this current, dear students? This current is equals to IE. What is IE? 1 plus beta f times IB. You know that. IE is equal to IB plus IC. So 1 plus beta f times IB. Now can you please let me know what is V0 here, dear students? Can you please tell me what is V0 here? Yes, let me reduce the size. Yeah, fine. What is V0, dear students? V0, current is moving away. Therefore, V0 is equals to minus beta f times IB into RC. What is Vi? This voltage is nothing but the voltage across here. So voltage with respect to the ground. The voltage which is Vi with reference to the ground. So apply KVL here. So Vi is equals to 0 plus IE into RE. Tell me dear students, Vi is equals to 0 plus IE into RE. So what I'm going to get here, what is IE? 1 plus beta F times IB into RE. Therefore, what is voltage gain? Voltage gain is nothing but output voltage by input voltage. What is output voltage? Minus beta F times, minus beta F times IB into RC whole divided by 1 plus beta F times IB into RE. So 1 plus beta F, I can take approximately equal to beta F, okay, because beta is almost like a 50 to 100 commonly in that range. So 1 plus beta F, if I take approximately equal to beta F, this could be neglected. So if I use that, gain minus RC by RE, oh my God, that's it, minus RC by RE. Sir, what is the value of RE? RE is nothing but, yes, I discussed already, VT by I EQ. That means what? To find the value of RE, I supposed to go for Q point current, that is DC current. But we need not to do. In this competitive exam, like KPTCL, they won't give this much, I mean to say, we need not to take this much time to find IEQ. They'll be providing the data in the question. They're providing what here? Data in the question. But if you could able to draw the circuit, how fast we are going to get, that is important. I'll just do one small circuit here. Now check it out, how fast you can do, okay? Very simple circuit. Students, I am taking a transistor circuit. I am connecting some external resistor, RE. Now here, I am connecting some resistor, RC. Here, I am connecting some resistor, which is RB. Now this is what, dear students? Plus VCC. Now this is the capacitor I am giving, which is Vi. And here, I am connecting a capacitor, which is V0. And this is ground. Forget about the circuit. This is the circuit given in the exam, let me assume. Now this is our circle. Correct? Now I need to find the gain. How can I find? I repeat, I need to find the gain. How can I find? Very simple logic. My dear students, right? See here, this is our transistor. See, this is the emitter. This is base, this is collector. Now here, simply I can go for what? Small RE. And here, current should always move from what? Collector to emitter. So this is what, guys? Collector. This is what, guys? Emitter. And this is base. There is no drop for a small signal. Correct or not? No drop for a small signal. That's it. What is inside the circle? Yes, it is completed. What is inside the circle? It is completed. Now externally, what I am supposed to connect? Externally. Yes, tell me dear student, externally. Capacitor will act as a short circuit. Yes, capacitor will act as a short, and here we are providing input voltage. Next, to the base, RB is connected. That should be grounded because I need AC signal, AC model. So this RB is connected to the ground. So from here, RB is connected to the ground. Correct. Next, emitter is connected to RE. Okay, this emitter is connected to what, guys? RE with reference to what? Ground. Okay, fine. Next, collector, short circuit to the capacitor and output voltage, yes, collector. No doubt here, we are taking the output voltage V0 because capacitor is short, fine. And collector connected to RC, other terminal is ground. So collector connected to RC, other terminal is ground. That's it, guys. This is our circuit. A simple circuit. Is that okay, dear students, right? So for our convenience, if I say I, let me assume this current is also I. Why? Because emitter current ideally equals to the collector current, base current I could neglect mostly in many of the cases, especially for our amplifiers, because beta we take in the range of 100 to 150, we can neglect for some situations. Now tell me, dear students, how can I find Vi? Let me know what is Vi. So Vi is equals to, speak out, 0 plus I into small re plus capital Re, that's it. What is V0? V0 is equals to, guys tell me, minus I into RC, that's it. Minus I into RC, it's over here. Therefore, what is voltage gain? Voltage gain is equals to minus I into RC whole divided by I into Re plus Re, which equals to minus RC by RE plus RE, that's completed, guys. That's it. That's a two-step answer. If you could able to draw this, we can, we will. Your art students, guys, your art students, you could be rocking for sure. So I believe you got the point or not. And what is this resistance? Dynamic resistance. And this resistance is inversely proportional to current. Resistance is inversely proportional to current, which is IEQ. And IEQ, you know that it is in the order of milliampere. Whenever this current is very large, this resistance will be very, very small. Very, very small. Mostly in the range of some 20 ohms to 100 ohms. Therefore, this capital RE, I repeat, capital RE will be in the range of kilo ohms. So this small 20 ohms, 30 ohms resistance, if I add with kilo ohms, I think you can neglect RE. So very fine answer. Simply voltage gain is almost equals to minus RC by RE. That's it, guys. That's it, completed. Minus RC by RE. Whew, I believe you got the point or not, dear students, right? How easy this is. Minus RC by RE. And this is what you consider it as emitter feedback circuit. Base bias with emitter feedback circuit. Previously it is a fixed bias circuit. This is base bias with emitter feedback circuit. Direct answers. For example, guys, if you see the question, let me show you one question. See, this is one question. I repeat, this is the question they have asked in the exam. Okay, now tell me, they are asking to find the small signal gain. See, this is our circle, this is our circle. Now directly can I get the answer? I repeat once again, directly can I get the answer? Yes, how? Simple logic. This is emitter feedback circuit. See here, take the transistor, this is our transistor. Here they have provided the resistor here. What is this value? 4.7K, which is RC, correct or not? What is this resistor? Tell me, guys. 3.3K, which is RE. Which is RE, right? And of course here some DC voltage they have provided, some AC signal they have provided. This is 4 volt, some AC signal, and yes, here V0, and this is plus 10 volt. Now they're asking to find the voltage gain, which is ground. Now how it is, how the circuit seems to be? Emitter feedback circuit. Just now I have solved that circuit, guys, correct or not? If I go back, yes, sorry. Yes, emitter feedback circuit. In this emitter feedback circuit, I just don't care about RB, whether RB is there or RB is not there. In the gain, that RB presence is not there. In the voltage gain calculation, that RB presence is not there. So directly I can use this formula as it is emitter feedback circuit. Or if you did not get this idea in the exam, I repeat, if you did not get this idea in the exam, no issue. We have that weapon of solving this circuit by using AC model. How can we solve, guys? How can we solve? Let me just compress. Yeah, how can we solve, guys? If you forget about the formula, how can we solve? See, this is our transistor. Simply it is RE, which is this external resistor. This is emitter. What is this external resistor, guys? 3.3K, ground, 0 volt, because AC drop is 0. Current always move from collector to emitter. Here, this is collector, this is base, and to the base, input voltage is provided because the DC voltage is 0, DC voltage drop is 0. Input voltage VI is provided, and to the collector, the resistor is provided here. What is that? 4.7K, and here it is V0. That's it, guys. Completed. So almost this current, if it is I, almost this is equals to I. Almost, approximate answer is okay. Because this is KPTCL, PSU, approximate answers are absolutely accepted. No need of getting afraid. Okay, guys. Now, can you please tell me, dear students? Please tell me. Therefore, the input voltage VI is equals to 0 plus I into RE plus 3.3K. So, which is equals to approximately equals to I into 3.3K, because this RE value is very, very small. So, approximately I into 3.3K. And what is V0? V0 is equals to minus I into 4.7K. That's it. The voltage gain is equals to V0 by VI minus 4.7K by 3.3K. That's the answer. 3 steps completed. That is minus RC by RE. Minus RC by RE. If you could remember that minus RC by RE, directly I can say voltage gain equals to minus RC by RE. That's it. Guys, okay. So in this way, you can solve a lot of numericals, not one or two. The similar method you can apply for MOSFET. The similar way you can solve the gain calculation. So guys, so I believe I think I have taken almost 1.5 hours. So thanks for your great patience. So in this short span of time, how much I could cover, I thought I have covered. If you feel that I went fast, I'm sorry for that. Please go through the previous video because it is a recorded video. We are uploading in the YouTube. Go through that video, repeat that video number of times. If any questions you have, we are always there with you guys. We are always there. And you know, my dear students, the ACE Academy. Students, yes, as I discussed already, we have the pre-recorded videos and we have the exclusive online live classes. You know, when is that? If you ask me, already the pre-recorded videos we have launched, dear students, 8th February 2022. So we have used different technologies like smartboard, glassboard, animations. We have taken a lot of effort to record the videos. Until you are in the subscription mode, you can repeat the videos a number of times. And you are having a great access that you can ask questions to the professors by using a separate feature. That feature I'll be explaining just within 1 minute mostly, guys. And also the KPTCL exclusive live batch also we have launched. That live batch, so 12th February for electrical engineering, 7th February for civil engineering. And the total details onto the screen over here. In the similar way, for live classes, I mean to say online, I mean to say recorded videos, for pre-recorded videos, guys, you can have the desktop version. I mean to say, we have the desktop version, laptop version, as well as the mobile version. Do one thing, I'll play this, I believe. Just go to the Google Play Store and type ACE Online. You will be getting the app, ACE Online, the app. Download that app, give your contact number, you will be getting an SMS, guys. Once you go with that verification code, you please check it out the videos. There, the KPTCL videos are absolutely uploaded there. You can watch in the mobile version. So you can even you can watch those videos in offline also. You can download in the app itself. You can watch those videos in offline also. Not only that, guys, even we have the laptop version. Even we have the laptop version. Yes, you can go with the laptop version. The same case, go to the Google Play Store and you can type ACE Online. You will be getting an app. Download that app. Just you select your KPTCL course over there. Then check it out. There are some demo videos for every subject, guys, free of cost. Demo videos are for free of cost. Go through those demo videos. You'll be getting a great conviction because the technology what we have used is like not a small scenarios. We have used very various technologies to deliver the classes. So go with that ACE Online. That is one beautiful product we have. Okay, dear students? No, sir, I go with the live classes. Yes, even exclusive live classes we have. ACE Academy is always for you guys. Any sort of doubts, we are always there with you. This is an organization running since 1995. It is not yesterday or day before yesterday, okay? 1995. Understand about the management and understand about the professors what we have. So we are always with you. May God bless you guys. Have a healthy and wealthy career and wish you good luck for your bright future. Thanks a lot. Namaste.